Hello students, we are going to see about calculus of residues in complex analysis. For that we are going to see some basic results, then we will do problems. This is result number 1. If z is equal to a is a simple pole for f of z, then residue of f of z at the pole a is equal to limit z tends to a, z minus a into f of z. I repeat, residue of f of z at the pole a is equal to limit z tends to a, z minus a into f of z. The next result what we have is, if a is a simple pole for f of z and f of z is of the form g of z by z minus a, where g of z is analytic at a and g of a is not equal to 0, then residue of f of z at the pole a is equal to g of a. The third result what we have is, if a is a simple pole for f of z and f of z is of the form h of z by k of z, that is we have a numerator and a denominator where h of z and k of z both are analytic at the point a and h of a is not equal to 0 and k of a equal to 0 means, then residue of f of z at the pole a is h of a by k dash of a. The fourth result what we have is, let A be a pole of order m greater than 1 and f of z, and let f of z is equal to g of z by z minus a the whole power m, where g of z is analytic at the point a and g of a is not equal to 0. Then residue of f of z at the pole a is equal to g m minus 1 of a by m minus 1 factorial. This is m minus 1th derivative of g of a by m minus 1 factorial. This is the first problem what we have. Calculate the residues of the given function. What we have is z plus 1 by z squared minus 2z at its poles. So we have to find the poles, then we have to find the residues at the respective poles. For that, first we have to find the poles. So what we have to find is, to find the poles. How to find the poles? In the denominator what we have, no, z squared minus 2z, let it be 0 and find the roots of the denominator. So which implies z into z minus 2 equal to 0. So either z equal to 0 or z equal to 2. So it has two poles. One is z equal to 0, the other one is z equal to 2. Since both terms are having power 1, these two poles are simple poles. These two are simple poles. If they have the power 1 means it is simple pole. If they have multiple power means we have to write the pole of order. If for example, if we have a term like z squared, then z equal to 0 is the pole of order 2. But here both are having power 1. So z equal to 0 and z equal to 2 are poles of order 1. That is, in short, we can call them as simple poles. Now we have to find the residue at both the poles. What we got as poles, z equal to 0 and z equal to 2. At these poles, we have to calculate the residues one by one. First, I am going to calculate the residue at the pole z equal to 0. The formula what we have is, what is the formula we saw? At z equal to a, if it is a simple pole means power 1. Simple pole means we have the formula residue of f of z at the pole a is equal to limit z tends to a. What is the pole here? No, here 0 means z tends to 0, z minus 0 into the given f of z. Okay. So here z equal to 0. So limit z tends to 0, z minus 0 into f of z. What is the f of z given here? This is our f of z. Z plus 1 by z squared minus 2z. I can take this z outside. So z into z minus 2. So what we have is z minus 1 into z plus 1 into z minus 2. So now z minus 0 is nothing but z, so we can cancel. Why we are doing this is because we are going to substitute, that is we are going to take limit z tends to 0, right? So we are going to substitute z equal to 0. When we have that term in the denominator, when I apply z equal to 0 in the denominator, anything by 0 infinity, right? So that is not we are not able to determine that value. So first we have to eliminate the term what we have in the denominator, then we can substitute that value, right? So for that only we are multiplying the factor first. When we multiply, both the terms will get cancelled. After that I can apply the limit. Okay, now we are not having any term z in the denominator, so easily we can substitute and we can find the answer. So come to the formula. When we find the residue of f of z at the given pole, here the pole what we have taken is 0, which is equal to limit z tends to 0, z minus 0 into the respective f of z. F of z is of the form z squared minus 2z, but I have rewritten that as z into z minus 2. Now we can cancel these two terms. After that what we have is limit z tends to 0, z plus 1 by z minus 2. Now we have to apply z as 0. So when we apply z as 0, 0 plus 1 by 0 minus 2, which is 1 by minus 2, which is equal to, finally it is minus 1 by 2. So residue of f of z at the point 0 is minus 1 by 2. Now we are going to find the residue at the second pole. What is this next pole we calculated? Is z equal to 2. So we are going to find the residue at z equal to 2. So residue of f of z at the pole 2 means limit z tends to 2, z minus 2. So whatever pole we have taken, no, that factor only we have to multiply. So z minus 2 into z plus 1 by z into z minus 2. These two terms will get cancelled. Now we have to apply, we have to substitute z is 2. So 2 plus 1 by 2. So 3 by 2 is the residue at this pole. So residue of z equal to 0 we got as minus 1 by 2, and residue at the pole z equal to 2 we got as 3 by 2. Is that clear? The same problem can be done using another method too. We have result number 3. No, in that if the given f of z is of the form h of z by k of z, a numerator by denominator. If we have a term like that, with the condition h of a, the pole what we get, no, h of a should not be equal to 0, that is not equal to 0, but k of a is equal to 0. When we substitute the respective pole, the denominator term will become 0 and the numerator should not be equal to 0. If these two conditions are getting satisfied means, then we can calculate the residue of f of z at the pole a as h of a by k dash of a. The first problem what we saw here, no, that can be done in this way, or using this result what we saw now, no, that can be solved in that also, but in both the methods we have to get the same answer. So we are going to redo the problem using the second result what we saw now, but anyway we have to find poles in both the cases. So I will take the poles here. One is z equal to 0, the other one is z equal to 2. Both are simple poles. This again we have to repeat when we start working in this method. But already we done, no, so I have noted down z equal to 0 and z equal to 2 or simple poles. Okay, so we are going to calculate the residue at z equal to, so residue at z equal to 0 first. Okay, so we are going to calculate. For that, first what is h of z? The numerator term what we have is h of z, z plus 1, and the denominator as k of z. K of z is equal to, it's a square minus 2z, right? So when we take for 0 means we have to substitute h of 0. H of 0 is 1, which is not equal to 0. But k of 0 is equal to 0, which is equal to 0. So the condition is getting satisfied. Now we can apply the result. So residue of f of z at the pole 0 equal to h of 0 by k dash of 0. That is the result we saw there, no? See the result. Residue of f of z at the point A is equal to h of a by k dash of a. A means the pole what we have here. A takes the value 0 and 1. So h of 0 is equal to, what is h of 0? Now only we got, no, that is 1. But k dash of 0, if we want to find, means first we have to differentiate the term and we have to substitute. What is k dash of z? I will do it here. K dash of z is equal to 2z minus 2. Am I right? So 2z minus 2. Then k dash of 0 is equal to 2 into 0 minus 2, which is equal to minus 2. So when I substitute here, it is minus 2. So minus 1 by 2. So residue of f of z at the pole 0 is equal to minus 1 by 2, which we got by using the previous method too, right? The same answer we got there, no? So next term is residue at the pole z equal to 2. So residue of f of z at the pole 2 is equal to h of 2 by k dash of 2. h of z is z plus 1. K dash of z is 2z minus 2. So h of 2 we have to calculate. H of 2 is equal to 2 plus 1, which is 3. And k dash of 2. K dash of 2 is equal to 2 into 2 minus 2, which is 4 minus 2, 2. So which is equal to 3 by 2. So the same answer which we got using the previous method. So either one method we can apply if we have a numerator by denominator, that is of the form h of z by h of z by k of z, means we can apply this. The next problem what we have is we are going to find the residue of z equal to 0. Here the residue is given in the problem itself, right? No need to calculate, right? Of 1 plus e power z by z cos z plus sin z. We saw the second method, no, when we have a numerator and denominator, that is h of z by k of z, we can apply that, no? Here we can do that, okay? So let me do that. Here given h of z. h of z is equal to 1 plus e power z and k of z is equal to z cos z plus sin z. We have to find what is h of 0 and k of 0. h of 0 is equal to 1 plus e power 0, which is equal to 1 plus 1, which is 2, which is not equal to 0. Am I right? Then k of 0. K of 0 is equal to 0 into anything 0 plus sine 0 is also 0. Sine 0 is also 0, which is equal to 0. So h of 0 is not equal to 0. H of 0 not equal to 0 and k of 0 equal to 0. These two conditions we have to check. After confirmation of these two conditions only, we have to move on to calculate the residue. So this is the formula. Residue of f of z at 0 is equal to h of 0 by k dash of 0. So first we have to find what is k dash of 0. This is k of z. First we have to differentiate with respect to z. Here we have two terms in terms of z. So uv method we have to apply. uv method, what is d of uv? d of uv is equal to u dv plus v du. So keep the first term as it is, differentiate the second term, that is minus sin z. Then keep the second term as it is, cos z, differentiate the first term z, that is 1, plus sin z. I'm sorry, plus you have to differentiate this term. This term when we differentiate, it is cos z. I repeat, this is a product of two terms. So keep z as it is, differentiate cos z. When we differentiate cos z, it is minus sin z. Plus cos z as it is, we have to take and differentiate z, that is 1. Plus here it is a single term. So sin z when we differentiate, it is cos z, which is equal to minus z sin z. Cos z two terms we have, no, so twice cos z. Now we have to find what is h of 0 and k dash of 0. h of z is 1 plus e power z, which is equal to 1 plus e power 0, which is 1 plus 1, which is 2, right? So k dash of 0, which is equal to, k dash of 0 means what? This is minus 0 into anything, it is 0, plus 2 into cos 0. Cos 0 value is 1, so 2. So this is 2 and this is 2, which is equal to 2 by 2. When we cancel, the answer is 1. So the answer for this problem is 1. So the residue of the given function is 1. Is that clear? Find the residue. The next problem what we have is find the residue of 1 by z square plus a square the whole square at z equal to ai. They have given the pole. In which pole we have to calculate the residue. If it is not given means first we have to find the poles, and in all the poles we have to find the residue. But particularly they are asking you people to find at this pole alone we have to find the residue. Okay. Let me explain how to find the pole if it is not given here. Here they have mentioned z is equal to ai. At this pole only we have to calculate the answer, right? Residue. But if it is not given, what we have to do? Take the denominator equal to 0. This belongs to the order of the pole. So don't bother about this. Take just this factor z squared plus a squared equal to 0, which implies z squared is equal to minus a squared. Minus a squared means it is I squared a squared. Am I right? So minus 1. Minus 1 is equal to I squared. Minus 1 is equal to I squared. So z is equal to plus or minus a squared I squared. So which is equal to plus or minus ai. So z is equal to plus ai and minus ai. So this can be z squared plus a squared. No. Z squared plus a squared equal to 0 can be written as z minus ai for this, and z plus ai for this equal to 0. So we have factorized like this. So z equal to ai is one pole, z equal to minus ai is one pole. But outside we have whole squared. No. What we have? Z squared plus a squared, the whole squared we have, right? So z equal to plus ai is a pole of order 2. Order 2. And z is equal to minus ai is also a pole of order 2. This is the procedure how we have to find the poles. Here in the problem they have particularly asking at z equal to ai. If it is not asked means at these two poles we have to find both the residues. But here it is not the case, right? So come to the problem, we are going to find the residue of the given function at z equal to ai. Already we know that z equal to ai is a pole of order 2. So z equal to ai is a pole of order 2. Am I right? This is the result we saw. If a is a pole of order m, which is greater than 1, more than 1 we have means the formula what we have is for calculation of residues, what we have is g m minus 1 of a by m minus 1 factorial. M minus 1 means m minus 1th derivative first we have to calculate. Then we have to substitute a, that is the pole. But in this case, what we have to take is g of z will be there in the numerator, and the pole, which respective pole we are going to calculate for residue, no, that will come in the denominator. Okay, so first we have to rewrite the given function in this problem in this order. So in which pole we are going to find z equal to a. So actually we are splitting this term as 1 by z squared plus a squared the whole squared, which is equal to 1 by z plus ai z minus ai the whole square. Am I right? Which can be rewritten as 1 by z plus ai the whole square into z minus ai the whole square. So in this pole only we are going to calculate. No, what is the factor for this pole? Z minus ai. This is the factor. So keep this term in the denominator, together all these terms together in the numerator. So I am going to rewrite this as 1 by z plus ai the whole squared by z minus ai the whole squared. So originally we are having this, but we have in this format only g of z by z minus a the whole power m. So whichever pole we are going to calculate, no, that will come in the denominator. Other terms we have to take in the numerator. So I have rewritten in this format. First I have split it into linear factors. Since it is having whole squared, separately I took the square. Then since for this factor only I am going to calculate the pole, I took the whole term in the numerator. Just we are rewriting. After simplification, this is the same term what we have here. Now we have to apply the theorem. Before that, we have to make sure g of a is not equal to 0, right? What is g of z here? This is g of z. G of z is equal to 1 by z plus ai the whole square. When I take z equal to ai, I should not get 0. So z equal to ai, when I take ai plus ai, it is twice ai, which is not equal to 0. So this condition is getting satisfied. So now we are going to apply this formula. So the formula residue of f of z at z equal to ai here is g m minus 1 of the pole a. Here the pole is ai. M minus 1 means ai is a pole of order 2. Already we calculated, no, it's a pole of order 2. Since it has power 2, it is a pole of order 2. So 2 minus 1 ai by 2 minus 1 factorial, which is equal to g 1 of ai by 1 factorial. 1 factorial is always 1. G1 means it is the first derivative of, we have to calculate g dash of ai. So before going to that, we have to calculate what is g dash of z. First we have to calculate this. Then we have to substitute z is equal to ai. What is my g of z? 1 by z plus ai the whole square. Am I right? So this term I have to differentiate with respect to z. What is the first derivative of this term? G of z, if you don't know the directly means, you rewrite this term as z plus ai the whole power minus 2. So denominator we have power 2. So I took that to the numerator as minus 2. For example, so what we have here is, for example, tell me if I have x power n, when I differentiate this with respect to x, what I get? N x power n minus 1. This is the general formula, right? So using that, this power is minus 2, no. So when we differentiate this, what we are getting is minus 2 z plus ai the whole power minus 2 minus 1, which is equal to minus 2 z plus into 1 will come ai power minus 3. So this can be written as minus 2 by z plus ai the whole power 3. So this is the derivative here. Minus 2 by z plus ai power 3. This is my g dash of z. In this, I have to take z is equal to ai. So g dash of z we got as minus 2 by z plus ai power 3. So in this place we have to take ai. So minus 2 by ai plus ai power 3. So minus 2 by ai plus ai power 3, which can be written as minus 2 by ai plus ai is 2ai power 3, which is equal to minus 2 by 2 power 3 a power 3 I power 3. What is I power 3? What is I power 3? I squared is equal to minus 1. I power 3 is equal to minus I. I power 3 is equal to minus I. So which is equal to minus 2 by 2 power 3 a cube into minus I. Minus minus we can cancel. So what we have here is 2 also, one term we can cancel. So 1 by 2 into 2, 2 squared we have no balance. So 2 into 2, 4, a cube I. What is 1 by I? 1 by I is minus I. We should not take I in the denominator. If we want to represent a number in the complex form, means it is of the form a plus ib. I should be there in the numerator, not in the denominator. So we have to convert 1 by I as minus I. You know how we are getting this? I will explain. 1 by I, multiplying and dividing by its complex conjugate. What is the complex conjugate of I? Minus I. So minus I by minus I, which is equal to minus I by minus I squared. I squared value is minus 1. So minus into minus plus 1. So finally it is minus I by 1, which is minus I. So 1 by I, you can keep in your memory as a formula itself. 1 by I. If we have I in the denominator, we can take that as minus I in the numerator. Okay. So I can rewrite this as, here I'll write 1 by 4a squared into minus I. That I am taking in the numerator. So I got g dash of AIS minus I by 4a cube. I'm sorry, it is 4a cube minus I by 4a cube. So final answer we have to write. What is the formula we have? This only we got as minus I by 4a cube by 1 factorial, it is 1. So the final answer what we got for this problem is minus I by 4a cube. So the residue for the given function is minus I by 4a cube. Is that clear? The next problem is we are going to find the poles of the given function f of z, and we are going to find the residues at the poles. So first we have to find the poles. How to find the poles? We have to take the denominator equal to 0. So z cube plus 2z squared plus 2z equal to 0. Since it is of power 3, we have to find 3 poles. Am I right? For that, all the terms are having z as common. So z can be taken out. Z squared plus 2z plus 2 equal to 0. So one pole is confirmed, z equal to 0. The other 2 poles only we have to factorize and find. Are we able to factorize this? Because the product of the roots what we have is 2 into 1 2, and the sum of the roots also 2. Product of the 2 means either we can take 1 2 or minus 1 minus 2. These are the two options, but both when we add we are not able to get 2. So we are not able to do directly, so we have to use the formula. What is the formula we know? For finding the roots, z equal to minus b plus or minus root of b squared minus 4ac by 2a. What is a here? A is equal to the coefficient of z squared, that is 1. B equal to the coefficient of z, that is 2. And c equal to the constant term 2. So using the formula, we have to calculate what is z. So when we substitute ABC values, we are getting this minus 2 plus or minus root of 4 minus 8 by 2. So which is equal to minus 2 plus or minus root of minus 8 by 2. Sorry, it is not 8. 4 minus 8 we have. No, it is minus 4. So minus 2 plus or minus, this minus 4 can be taken out as I into 2. Right? Already I told you I squared is equal to minus 1. So root of minus 1 can be taken as I. And for 4 we can take the factor 2 by 2, which is equal to, both the terms are having 2 common. So minus 1 plus or minus I by 2. 2 we can cancel. So we got two factors as minus 1 plus I and minus 1 minus I. So we can we can write the factors as z minus of minus 1 plus I and z minus of minus 1 minus I. Am I right? So this can be rewritten as z, when we multiply minus inside, plus 1 minus I. This is one factor. This is z plus 1 plus I. So we have splitted. So the poles what we got here is minus 1 plus I, minus 1 minus I. Already we got 0. So totally 3 poles we got. So these are the poles we got. Poles are 0, minus 1 plus I, minus 1 minus I. All are simple poles. All are having power 1. So that is simple pole. F of z is equal to the given f of z, this thing. I have rewritten that as, I have splitted that as 3 factors. The one factor is z, that is for pole 0, and this is for this pole, and this factor for the third pole. So I have rewritten. This is of the format h of z by g of z. If h of z is not equal to 0 and g of z equal to 0 means we can proceed with the result what we saw earlier. This is the result what we saw. Residue of f of z at the pole z equal to a is h of a by g dash of a. So for that, first we have to make sure h of z is not equal to 0. One by one we have to check. At the pole 0 means when we substitute z equal to 0, it is not equal to 0 alone. So every term we have to one by one check and we have to proceed. At 0, strictly h of 0 is not equal to 0. So we can proceed with this formula. Okay. So for the pole z equal to 0, we are going to calculate what is the residue. So h of z is equal to z squared plus 4, g of z is equal to this thing. When we take z as 0, this is 0 plus 4, which is not equal to 0. Okay, so we can proceed further. We have to calculate what is h of 0. H of 0 is 0 plus 4, which is 4. G dash of 0, first we have to calculate, no. For that, we have to differentiate g of z. G dash of z is equal to 2 z squared plus 4z plus 2. So g dash of 0 equal to, this is 0 plus the 0 plus 2, which is finally 2. So it is 2. 2. So the residue for f of z at 0 is 2. So the next one is residue of f of z at minus 1 plus I, which is equal to h of minus 1 plus I by g dash of minus 1 plus I. So h of z, what we have is z squared plus 1. Sorry, z squared plus 4. So it is minus 1 plus I the whole square plus 4. Am I right? So which is equal to minus 1 the whole square plus I squared plus 2 into minus 1 plus I. Or else you can rewrite this as I minus 1 the whole square plus 4. Now you use a minus b the whole square formula. A squared minus 2i into 1 plus 1 squared plus the last term 4. I squared is minus 1 minus 2i plus 1 plus 4, which is equal to minus 1 plus 1 will get cancelled. So minus 2i plus 4. So here h of z we are getting as 4 minus 2i. So 4 minus 2i by g dash of minus 1 plus I we have to calculate. So what we got as g dash of z? Here we got 4 minus 2i. Is that clear? G dash of z we got as 2z squared plus 4z plus 2. In this we had to substitute the pole. The calculation will be so lengthy, right? So g dash of z is equal to 2z squared plus 4z plus 2, where z is equal to minus 1 plus I. It is not 2z squared, it is 3, because z cube we had no. So when we differentiate, it is 3. So 3z squared plus 4z plus 2, 3 into minus 1 plus I the whole square plus 4 into minus 1 plus I plus 2. This we can expand using a minus b formula. This is the whole square plus this we can multiply, we will do later. Minus 1 plus I plus 2. Now we expand 3 into I squared plus 1 minus 2I plus when we can multiply this, no, this is minus 4 plus 4I plus 2. So which is equal to 3 into this is minus 1 plus 1 minus 2I. These two will get cancelled. Minus 4 plus 4I plus 2. So which is equal to, when we multiply, this is minus 6I minus 4 plus 4I plus 2. So which is equal to, we can combine these two together as minus 2I, and we can combine these two together as minus 2. So minus 2 is common, I plus 1 finally. So now we are going to substitute in the formula. H of minus 1 plus I we got as 4 minus 2I, and this G now we got as G dash we got as minus 2 into I plus 1. Minus 2 into I plus 1, which is equal to, numerator is having 2 as common. So 2 into 2 minus I by minus 2 into I plus 1 2 we can cancel. When we have a complex number in the denominator, we have to multiply it by its complex conjugate. What is the complex conjugate of this? 1 minus I. In this part, we have to take a negative sign. So 1 minus I, 1 minus I, which is equal to this minus I can take to the numerator, minus 2 minus I in by, this is a plus b into a minus b formula. So a squared minus b squared, I squared, into the numerator term 1 minus I we have. Am I right? Multiply this minus inside. So minus 2 plus I into 1 minus I by 1 squared minus I squared is minus 1. So minus into minus plus. So finally in the denominator we will have 2. So when we expand this, minus 2 plus 2I plus I minus I squared by 2. This is minus 2 and this is 3I. I squared is minus 1, minus into minus plus. When we add these two, it is minus 1 plus 3I by 2. This is the final answer. So we got the answer, that is we got the residue at f of z I is equal to I minus 1 is minus 1 plus 3I by 2. One more residue, one more pole we have no minus 1 plus I. In that also using the same procedure we have to find the residue, and I have given the answer for your verification. Use the same procedure what we did for the second pole and you have to get this answer. Is that clear? Thank you.